need to measure high voltage and low voltage? So basically just measure the voltage.
So you want it to be a voltmeter, basically?
Yes, yes.
Okay, so I can go over here, it's saying it's not connected. Wait a minute, why is it, it's not? Oh. We gotta connect it to a piece of hardware, so we got SMU1, what is this other one? This is SMU2, so we'll make this SMU3.
Yes.
Okay, now we can say, you want a voltage, okay, let me explain one thing about SMUs. If you want to use an SMU as a voltmeter, you still have to source something.
It's going on.
An SMU always has to have a source function. Okay, that's one of the gotchas with an
More
SMU.
close?
So to make an SMU into a
Alright,
voltmeter,
no,
you have to
then I
source
need to
0
refocus
amps.
everything.
To make it into a current meter, you source 0 volts.
Okay.
That's how an SMU works. It always has to have a sourcing function. Okay. So if I want to measure, a voltage here, I source a current.
Okay.
So
So
I come
current
here,
source,
and
current
I say
bias.
current bias, and I put it at 0, and it's gonna see now I can measure voltage.
Okay.
Okay, so
Okay.
now that's a voltmeter. So now what? And if I set up another pin to do the same, it'll measure them both at the same time.
Yeah.
It'll apply your current bias and measure the two voltages at the same time.
Perfect.
For SMU1,
For us,
we do source current, right?
it's yes, it's
If we want to inject current. Right?
yes. So current bias is the. I didn't put anything in.
The
We have to put
bias
something.
should
Yeah.
not be zero.
No, it should not be 0. You got to put something. You got to put something in there, obviously. Yeah. Yeah.
You actually want to sweep your current, right?
Yeah.
Yeah. This instrument shines on sweeping. It's a sweeping instrument, okay? Which brings me to a point that I want to make because a lot of people don't get this. The fact that it's a sweeping instrument, some of the things you're used to doing, you might have to change your thoughts on. For instance, everybody knows what auto range is, right?
Auto range?
On a scope?
On a scope,
Oh,
on
okay.
any instrument, right? Forget about auto range. Auto range is dangerous on a sweeping instrument, and the reason it's dangerous is because when you're sweeping a measurement, sometimes you're gonna go through a large dynamic range, which is gonna cross over several ranges, right? Well, the DCSMU has built-in delays that are range dependent. So when you change ranges, your timing changes. And what you're going to see in your sweep is a little blip, and you're going to call me and say, there's something wrong with my system, it doesn't work. Well, no, it's working fine. It's that that range change takes time. So it's going to interrupt your nice, beautiful sweep, and it's going to give you some artifacts in your sweep that you're going to think are wrong. They're not wrong. That's the way it's supposed to work. Because the lower the range, the longer it takes to settle the measurement. So there's delays that are built in. It's because of Johnson noise. You familiar with Johnson noise?
I have them.
Yeah, you're not familiar with Johnson noise? Okay, so what Johnson noise is, any conductor, it has some inherent noise because of the movement of the majority carriers, usually electrons, in the material itself. And they're just, even in a steady state, there's movement of majority carriers in the material. That's noise, okay? And if you're trying to measure small signals, that noise can swamp out what you're trying to measure, right? So the smaller the signal, the more problem you have with Johnson noise. So you have to wait. You have to wait for the signal to stabilize, okay? So, for instance, because of Johnson noise, there's certain measurements you can't make. If the Johnson noise line, on the voltage side, it's like this, right? So if you're trying to make let's say you're trying to make a picoamp measurement in a picosecond, you can't do it. The Johnson noise graph, if you look at a Johnson noise graph, it shows you that it's not possible.
So I need to increase
Okay.
the time.
It's done for you, for the most part.
Okay.
That's what I'm saying. That's why your sweeps will get messed up because of the timing change as it spans different ranges. It will change the timing for you mid-sweep, which you probably don't want. Okay, so or maybe you do, because there's a consequence to that as well, because the instrument's always most accurate on the lowest range. So if you set a fixed range, you're going to have to set the fixed range at the highest range of your sweep, right? Which means on the low end, you're going to have less accuracy than you are on the high end. Because your accuracy is going to be based on the range you're set on, not on the measurement you're making. It's based off of the range. So if you look at any data sheet on any piece of equipment, a DMM, a power supply, an SMU, it shows you all the ranges, and there's a different accuracy spec for every range, right? So your accuracy is going to change during your sweep, which you may be okay with that, you may not be. And if you're not okay with that, then use auto range and deal with the blips in the data. You just have to deal with that. Or you can break up your sweeps into smaller, keep it within the range. Yeah, well, that's what you're seeing.
Right?
Yeah.
Remember some blips
Okay.
at the same time.
And the reason you're seeing, the reason this is an issue is because that's the way a DC SMU is designed. A DC SMU is designed to give you the most accurate voltage and current sourcing and measuring that it can. And that's the way it does it. It doesn't care about timing. Timing is secondary. Okay, it kind of ignores timing. That's why you don't see absolute time values posted. We talk about factors, time factors, because it's kind of indeterminate. We don't really know our timing. Okay, if you want to know your timing, you have to do a sweep and you have to enable timestamps, and it will put a timestamp on every reading, and you can go back and you can look at the timing, but you can't necessarily decide ahead of time what timing you want because you don't know, because it doesn't care.
So when we
If you want accurate timing, you need a pulse instrument. You need a pulse card. A pulse card now, it's the opposite. Its focus is timing and a little less priority put on voltage and current accuracy. Okay, so the deal is an SMU has an analog feedback system where so let's say you want to source 2 volts to your device, and you've got remote sensing, where you bring the remote leads to your device. And the device, when the first time it sources 2 volts, the device sees 1.9 volts. It's right away going to say, oh, that's not right. I'm going to turn up the voltage to source another 1/10 of a volt, and I'm going to remeasure until I get the voltage that you want at your device. It's going to do this feedback loop until you get that voltage. So that there's a timing indeterminance there, because you don't know how long that iteration is going to take, right? Or how many iterations is it going to take to get you what you need? So there's you really can't rely on timing in that situation, because it's
so
going to.
when it shows the graph, I mean, we have the sweep or anything. So it's not real time. It's not doing the exact same.
When it shows you the graph, it is real time. If you turn on timestamps, you can see the real time. But I'm saying if you try to determine ahead of time your timing, you probably can't do it, right? You probably can't do it. You might have to do a sweep to see what your time is, okay? Now with a pulsed instrument, it's the opposite. When you define timing, it sticks to it. It doesn't care if you violated, if you got overshoots and you got ringing, whatever. It's going to finish the sweep before it's going to do any adjustments. So you got to do a complete sweep. Then you got to make a change and then do a complete sweep again, because otherwise it can't maintain timing, accuracy. Okay, so there's different instruments for different purposes. The DC SMU is designed for real accurate IV curves, where you need accurate voltages and currents. That's what it's designed for. Timing, not so much. You might even have to hook up a scope if you really want to see what's going on from a timing aspect. Now, here's another point. You hook up a scope right to your device, you're loading down your measurement with the scope. There's a trick. There's a trick to avoid that. And that's what the third conductor is on the triax cable. Triax cable has a conductor called a guard. The guard has a unity gain buffer. So whatever you're sourcing down the center conductor gets turned around in the instrument, gets put through unity gain low impedance buffer, and it outputs on the guard. So the guard is driving the same voltage as your center conductor, so that's where you put your scope. So now you buffer it from your device. That's a trick that a lot of people don't know. But that's a good way to be able to hook up a scope without it loading down your circuit. Okay, if you want to do that.
Unfortunately, the settings. So here we have set that 1 to count, right? So the voltage per count.
This one? Yeah.
So for the current, you should set another column for current to go to the ground, right?
Well, it's going to flow. It's going to flow from here to there.
So we need to do no need to.
That's another good. There's another good point. Any of you guys use Keithley individual SMUs in the box? Like 2600, 2400s. Okay. There's a significant
Yeah,
difference.
that's the one you've used.
Yeah.
There's a significant difference
one,
between
right?
those and this, and you should know the difference. The difference is those are floating. The grounds on those float. So you can put the ground above. You don't have to be on a ground potential. You can put it away from ground, up to 250 volts or something big number. These aren't floating. Every SMU in this box is common grounded internally. So you cannot do an off-ground voltage measurement. You have to do a differential measurement. So you need 2 SMUs to do that, right? You understand that, right?
Mm-hmm.
And you have to subtract.
Yeah.
To subtract 1 from 2. Okay, does
And
that
it
make
does
sense?
that for you. It does that for you, right?
You have to set it up. There's a formulator that you can do the math with, and I'll show you that.
That would
Okay,
be
so the formulator allows you to post-process. It'll give you the 2 voltage readings in a separate column on your data sheet,
Mhm.
but then you've got to write a formula that says, take V1 minus V2 and give me another column of that data.
Or you can export everything to
Well,
Excel.
you can export everything and do it in Excel, but this has got some pretty powerful features, though.
Yeah.
You shouldn't need to do that. It's got a lot of, the formulation is a very powerful feature that allows you to do a lot of neat stuff. Okay, you can find slopes, you can do line fits, you can do regressions, linear regression. You can do a lot of stuff right on the machine. Okay, so you just make sure you understand that it's ground. That's why if you want to do Vanderpool, anybody doing Vanderpool?
No.
Yeah. Yeah, we'll be doing.
If you
some
want to do
Vanderpool.
Vanderpool,
I tried number 4.
you need 4 SMUs to do it.
Yeah.
Because you can't just, you have to have an SMU on each pin, is what you gotta have. Because you can't just put a ground on it. You have to, it's not floating, so you have to reference everything to ground. So you're gonna source a current across 2 points, you're gonna measure 2 voltages and subtract them. That's how you gotta do it, to get that voltage across your material, right? Okay, so that's important to understand. Now, we're just talking about speed and timing. We talk about speed. We just give you, quiet, fast, normal, quiet, or custom. We don't
Sort
give
of
you
quality,
numbers.
right?
Yeah. So there's an important thing to know here in that there's the source measure cycle. We call it an SDM. Stands for source delay measure, and all 3 of those processes have time delays associated with them. The source, for instance, when you set a source value, there's the built-in delay we just talked about. It's range dependent. You can't control that. When you set a source value in a range, there's a certain amount of delay that comes with that. Okay, so then there's the delay portion of that is your delay. You may want to add more delay. So you can go in there and add additional delays. Typically it defaults to 0, but if your device is highly capacitive, you might have to wait longer than the default delay, so you can add more delay. And then the measure has another delay as well, and that's what we're talking about here, measure settings speed. So that's, it uses a integrating A to D converter. So what it does is it samples at a very fast rate over a period of time that you determine, okay? So we use the power line cycle frequency as the base for that integration. And why do we do that? Because most of your noise in your measurements is 60 hertz noise due to your fluorescent lights, right? So if we integrate over 1 over 60, 20, or 16.67 milliseconds, and we give you an average, we've eliminated 60 hertz noise. Make sense? Okay, so what that means, that's what normal is. Normal is 1 power line cycle. So if you're at 50 hertz, it's 20 milliseconds. If you're at 60 hertz, it's 16.67 milliseconds. So if you want a good, clean measurement, you probably want to be on normal mode, which means that you're not going to get a measurement any faster than 16.67 milliseconds. But you're going to get a good measurement. You get a good, accurate measurement. If you want a faster measurement, we can set this to fast, and it'll go less than 1 power line cycle. I think it's 30% less. Custom allows you to set any value you want. Okay. Quiet goes 30% slower, right? So you got to understand that's the A to D aperture time for the measurement. That's how long it's going to integrate for your measurement, because all your measurements are riding on an envelope of noise on your ground that comes through the power line, right? So that's one way we can give you nice, clean measurements. The point here is that there's a trade-off between speed and accuracy, and it's just physics. We can't solve that for you. So you have to decide what's your tolerance for noise. If you want a very fast measurement, you don't care about noise, you can set this very fast. You can set the MPLC value to like 0.0001 or some real small number. Okay.
So when we say fast, how fast does it mean? Is there a number
It's
associated?
1.3 power line cycles. So it's 30% higher than normal.
But then if you integrate over not a whole cycle, right, don't you get some of the...
You're going to get some of the noise.
Right.
Correct. Correct.
So it's actually worse then?
Yeah, it's worse,
Okay.
but you can go 10 power line cycles if you want.
Right.
And that's like a digital averaging, right? So now you get a real clean, stable measurement, right?
good
Because you
enough.
can go multiple power line
So
cycles.
And that would be the custom one, right?
Yes.
The same, right.
So my point here is you should probably just,
So
for the
normal.
most part, stick to normal. Why would you need to go faster? What if you're in a production environment and you're on a wafer that's got 100,000 sites and you need to test every site, right? Every millisecond's going to matter in that case, you
Well, in
know.
our case, sometimes you want to check how good your probing is. You just want to really quickly run it, and then because then also the measurement is slow if you don't have a lot of current, if you don't have a good
Yeah,
connection.
but in
you know,
this
stuff like
environment,
that,
what's the difference between, 1.6 milliseconds and 16 milliseconds? Is that going to really matter to you? Probably not. So wait, get a better measurement. Wait longer and get a better measurement.
Well, I'm saying when you don't really make a measurement, when you just want to see, am I connected to the device or not, or, stuff like that. But,
Yeah.
but you're right, yeah.
Yeah. Yeah. So you have the patience here to wait a little longer for your measurement, is my point. Production people don't have that patience. They need everything as fast as they can. So what they're going to do is they're going to source a voltage to their, before they figure out their timing, they're going to source a voltage to their device, and they're going to measure the current over time, and they're going to watch it charge up, and they're going to decide where do I need to take my measurement? Where's the earliest I can take my measurement? And they'll look at the timestamps and they'll put that in. That's what they'll do. Okay. For you, just let it go, because the longer you wait, the better the measurement you're going to have, right? Because it's asymptotic, right?
Right.
Typically, they say you want it to be within 2% of the final asymptotic value is considered a good measurement. But you put an edge on a device, the device doesn't see an edge. You know what it sees? It sees a charging curve, and it's not necessarily due to the device. Sometimes it is, but it's due to everything. It's due to the cabling. It's due to if you got a chuck. A chuck is a big capacitor, right? So everything that's connected between your hardware and your device is it's contributing to that it's adding to that RC, the C portion of that RC time constant, which is gonna. That's why I say keep your cables short, right? Because every foot of cable has so much capacitance. The more cable you got, the more capacitance you got. Okay. Now there's.
I have a question. You said that you also have a problem with that connectors there. So is it better to use a longer wire and connect the probes directly to the SMU, or use another wire and connect them?
Here's what's best. You have a remote preamp in the back here. I don't have it mounted remotely right now. It's designed to be mounted remotely. If you have 4 remote preamps, here's the ideal setup. You got the CVIV box. All your preamps are in the box. That's your measurement hardware. That's your A to D hardware. It's in the preamp. It's not in here. It's in the preamp, right? You put that right here, okay? And then these cables go directly to the CVIV box. Now you've eliminated this cable completely, right? And you've eliminated this bulkhead. That's ideal, okay? Ideal is that's one of the purposes of the CVIV. It's designed to be put on your table right by your probes, okay? And most people when they order probe stations, the probe vendor asks them, how long do you want your cables? Oh, give me 2 meters. No, that's a bad idea. You want these to be short. I like to see them, this long. That's what I like to see. You can also take the preamp that's on the back here, the little black preamp on the back. We provide you a cable that can go between the SMU and the preamp, and you can bring just that preamp on here as well. And you can lay it right here and have a cable this long. And if you're not measuring below 100 nanoamps, it doesn't matter. But if you're measuring femtoamps, attoamps, it does matter. Okay, so that's important.
We don't even do femtoamps.
You mind if you have like off current of a transistor or something, but then you can bring it out for one SMU, like your most critical one.
Exactly.
And you just put it there.
You only have one preamp, so you would use that one. Yeah.
Mm.
Yeah. Okay, everybody understand that? That's the ideal setup. And also, if you want to measure attoamps, you need to do more than just that. You need to have shielding.
Well, it's the whole box.
The whole box
Yeah.
needs to be shielded because because just going like this will give you a noise. It'll give you noise
But it
from
is
the-
a shielded environment, right?
What's that?
The probes, it is shielded.
The base.
Oh, it's shielded, yeah. You're right, it's shielded. Yeah, this is a pretty decent setup. This
And I
one
actually-
won't be.
I actually think this door also has a switch for the 100.
Does it?
I think. Open it. Try it.
Yeah, this one.
It's like some,
Like a magnetic switch or something? No, it might. You should have a connector then, coming out of it somewhere.
So there is one here.
It might
There's a
have it.
connector.
It might have it.
It is connected there.
Does it say interlock on it or something? There's a cable.
So this, yeah.
Probably a magnet right here. It probably does.
So you,
It probably does.
you could actually connect this
Yeah,
to
this
your
one- this
interlock
one- yeah,
maybe
this-
on
this-
the SMU, right?
This shields you from being able to touch the device, so this
Yeah.
one might be doable to set up that way. But you got two machines, and one doesn't, and one does, so don't use it.
Yeah, yeah.
I mean, this will protect you unless something's wrong with the pro bus or something,
Right,
right? And
right.
you get shocked. You can also wear gloves, might help, right? But
Okay, now I forgot where I was going with this. There's another feature that you have here using the triax cable and the guard, right? We talked about using it's a driven guard, so we can take, if I'm sourcing a voltage to my device through a lot of capacitance, my probe station, my cabling, and that's a problem for me because there's leakage through the cables, and there's the capacitance of the cables, so your timing will be affected as well as your accuracy because of the leakage. The triax cable allows you to do what's called guarding. And what a guard is now what I can do is I can source through that buffer, I can source a driven voltage to the guard, which is the same potential as what I'm sourcing to my device. So what has that done in effect? It has shorted out my capacitance. I get 0 volts across my cable. Capacitance is gone, your leakage is gone. Leakage isn't gone, but it's sourced by the buffer, so it's not part of your measurement. Okay, so that's another way to improve your measurement capability. If you've got high leakage cables or chuck, that's one way to deal with that. Use the guard. We call that a driven guard.
do you set that up in the software, or how do you?
You just wire it up, it knows. It detects. It detects it. It doesn't. The guard is always driven. It's always going to be driven. But a guard is not like shielding. Okay, a shield is terminated. A guard is not terminated. Okay.
If you want to measure capacitances, do you need to like preset the inner capacitance? on
Yes,
the
that's called compensation. Do you need to see how to do that?
Yes, please.
Okay, I can show you that. Okay, so let's say I'm gonna go to the CV MOSFET test. I'm not gonna save this. Okay, so, your point is that there's capacitance and everything that you don't want to be part of your measurement. We need to take that out. We need to reference that out. It's a two-step process. Make sure you get that because a lot of people don't get that. You have to do the compensation. You have to enable the compensation. If you don't enable it, it doesn't happen. Okay, so what you got to do is you got to go up here to Tools, and you see here there's Connection Compensation, and there's really 4 things that could need to be compensated. One is the cable length, because there's a phase phase situation here, right? And if your cables are different lengths on your CV meter, you'll get a phase error. And if that phase error is greater than 90 degrees,
Then you
it
get a full
freaks out.
phase shift. Yeah.
Yeah, you get a mess. So make sure you always use the same cables that we provide because this is already set up for those cables. It's 1.5 meters. These are 1.5 meters. There's open compensation, there's short compensation, and then there's load compensation. Forget about load compensation. You should never need it. You would need to do open compensation if you're measuring small capacitances, and you need to do short compensation if you're measuring large capacitances. Okay, so most people, all you really need to do is the open compensation. Okay, so what you would do is you'd have everything connected to what your device could be in. You drop your chuck and you run that. So everything's cabled to your device. And what you're going to do is you're going to measure the capacitance that the system sees without your device being connected. Okay? And what it's going to do is it's going to go through every range, every frequency, every voltage range on the CV meter. So it takes a little time. And it's going to run through all the ranges, and it's going to measure capacitance, and it's going to store that internally on the card. That's all it's going to do. It's not going to reference that to any of your measurements. It's just storing the values. That's what this does. Okay. Once you do it, you should never have to do it again unless you change something. Right?
Open was for low caps, right?
Low caps, right? Because the capacitance of your cabling and stuff is going to be low, right? But if you're measuring low capacitance, it could matter. It could affect your measurement, right? So you want to know what that is. If you're measuring a large capacitance, it's like a short almost, right? So to do short compensation, what you got to do is you got to short your probes. Okay, so what you basically do is just drop both your probes on a pad, on the same pad, and run short compensation. And that'll measure the capacitance with a short. Okay? So that's only if you're measuring large capacitances, microfarads, type ranges. So you can do them all, doesn't hurt anything, but the short capacitance, the short compensation really won't affect your small capacitance readings. Okay? So you can do them all, and then you can decide within your test which ones you want to enable. Okay? So now that I've done this, the advanced compensation has the load, where you got to put a load of like 50 ohm load on, and which we don't even provide because nobody needs it.
Because this goes up to 10 megahertz.
Goes to 10 megahertz.
So you don't need load at that frequency yet.
Right.
Yeah. And so you want to do this every time you change anything, any cable or.
If you change cables, or you add an adapter, add some more cabling, from here to, whatever. If you're always set up the same way, you do it once and be done with it. Probably doesn't hurt to do it every now and then, though, just to be sure. Something might change. It probably doesn't hurt.
You don't know who used it the day before. You just do it
What's
at
cool
the
is
beginning of the day.
What's cool is do your CV test with the compensation and without. You can see then you can see the difference. That's usually an eye opener for people when you see that. So we do the compensation for the CV card itself, and then when we go to the test, if we go over here, here's where we enable it. If I want to add open compensation to this test, I just check that, and then it will use the values that are on the card. Yeah, before you run the test, you just select open compensation.
Does it hurt to just select both? Like even if you say you don't always need it, but
as long as you run them.
As long as you run them, right? You can select both. You're on the safe
there's
side.
no harm. There's no harm in doing that. No.
Okay.
No. But that's how you.
Open is open and short, right?
So basically you then just select both of these, open and short.
Yeah.
And then for this test, it will use those stored values that are on the card. If you don't do that, it ignores it. Okay? Make sense? And here's if you change cable length, you can actually do that here as well. Okay. You're familiar with the different models, the different capacitance models. This is important because I have customers that are designing MOS caps, for instance, and they'll make a cap structure, and they'll do a CPG piece type test on it, and they'll call me and say, something wrong with your system. I mean, doesn't seem right. So what I'll tell them to do is run the Z theta.
You cannot sit
Run the Z theta check, and what we see is above a certain
specific.
frequency, their phase angle goes off at 90 degrees and starts dropping. So what they essentially built is they built a capacitor up to a megahertz. Above a megahertz, it's a diode. And so it's, it could be their device, but they don't know it unless they do that test, right? So sometimes you might have to see that. You make sure you've got a 90-degree phase shift between current and voltage, and you know you have a good cap, right?
Or you might get inductance from.
You might get and you can measure inductance as well. We can give you the R plus JX, real and imaginary value. You can calculate anything you want. Yeah. So any complex impedance you can calculate if you have that, right?
Basically, Z and theta is always right. It's just the impedance it measures, right? And then you can fit whatever
The
model
other
you
thing
want
is
to it.
the dissipation factor is important too, because you know what happens if you got a high dissipation factor, right? That means you got a leaky cap, which means your capacitance. It means your capacitance measurement is not good. So you should probably do that first. Make sure you've got a low dissipation factor, because if your dissipation factor is high, the results of your other measurements are probably going to have a lot of error.